Tonight in Arkansas, there's a mother tucking in her daughter and turning off the light. A business owner's burning the midnight oil. An at-home dinner date is plating up possibility. And it's all happening under one roof. How? The power of a conversation, like the one John from Integrity Solutions had with First Horizon Bank about his vision for a sustainable mixed-use building. Now it's not just words, it's life. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John. First Horizon Bank, member FDIC.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast known as Space Nuts. I'm your host, Andrew Dunkley, and joining me, as always, is astronomer Fred Watson. Hello, Fred.
Hello, Andrew. Fancy hearing you coming across the airwaves.
Yes, it's a bit strange, really, isn't it?
It's strange, yeah.
Out into the ether. And
nice to talk to you.
You too, as always. Today we're going to be discussing another confirmation of general relativity, and this is a huge story and one that I know you've had a lot of interest in for a very, very long time.
Indeed.
In fact, I think you actually were the first person to approach Einstein about this. And
something like that, yeah.
We're going to look at radioactivity in space. There's been a revelation there. And we've got a question. Good grief, we have a question from Richard Goodman, who sent us, a biblical edition of his question. If I start reading it now, we might just squeeze it into the entire episode. But look, what we'll do, Richard, is we'll try and tackle portions of your question and maybe do the rest another time. I think that would be fair. But we'll see how we go. But we might... Richard actually asked a question about the galactic view, depending on where you are, which would be a fascinating thing to discuss, and a follow-up on the discussion we had recently about the new moons of Jupiter. So we'll try and tackle those two, and we'll deal with the other 50,000 questions down the track. But first, Fred, confirming relativity. This is a cataclysmic story of epic proportions.
Yep, this is a story I've been following. Well, actually, for a large proportion of the time that it's been running. This is a study that's been going for 26 years. I only caught up with it a decade or so ago, so I'm a relative newcomer to the problem. But it's work that's led by a German scientist whose name is Reinhard Genzel, and Reinhard works for the Max Planck Institute for Extraterrestrial Physics in Garching in Germany, which is it's actually a suburb of Munich. So what he and his team have been doing for the last 26 years is observing a group of stars which are in orbit around the supermassive black hole at the middle of our galaxy. So it's pretty extreme work that he's doing. Now, one of the issues that's confronts you immediately when you start tackling work like this is that in optical telescopes that use visible light, those stars are invisible because the direction to the center of our galaxy is blocked by clouds of dust. There's dust clouds in the spiral arms that are between ourselves and the galaxy. And that's why we don't, when we look at the night sky, the center of our galaxy is in the constellation of Sagittarius, which passes overhead from our latitudes here in Australia. And when you look at the Milky Way in that region, it's very wide because you're seeing the kind of bulge of our galaxy, which is, the fat bit in the middle. But the view to the center itself even though there are star clouds there, the star clouds of Sagittarius are glorious on a winter's night, you are still finding the view blocked by dust, so you don't see all the way to the galactic center. This harks back to work I did, actually, in believe this or not, the 1970s. I worked with a scientist at the Royal Observatory in Edinburgh, and we were looking for stars which were sort of circulating around the galactic center, but nowhere near as close to the middle as the Gensel stars are. So what do to penetrate this dust? They use infrared.
Oh, okay. I was thinking radio telescopes, because they are able to do. You get past some of these blind spots, and there are massive numbers of blind spots.
There are, yeah. So radio telescopes would also penetrate the dust, and that's how we know that the black hole is there, actually, because it emits radio emission as stuff swirls into it. But you can't see stars with radio telescopes because they're radio quiet. But you can with infrared telescopes. And so this team has poked through the dust clouds with infrared radiation, and observed over a long period of time with very high accuracy this group of stars very close to the supermassive black hole. And what they've done over the 26 years is been able to plot the orbits of these stars as they circulate around the black hole. It's quite extraordinary stuff. When you watch a movie of it, it's like these sort of moths fluttering around something that's not there because you can't see the black hole in the infrared. And in particular, they've looked at one star, which is the star that passes closest to the black hole. You would think that would have a special name. I always think it should be called Proxima Galactica.
Oh, yes, very good.
Yeah.
They should employ you.
Yeah, they should, because
name things.
Actually is called S2, which is to distinguish it from S3, S4, S5.
Yep.
And, I'm hazarding a guess here, Andrew, but I wonder if the S might stand for star?
Well, it could.
Yeah. So star number 2. Star number 2 comes within 20 billion kilometers of the black hole itself. And that's pretty close. I mean, remember, in our solar system, Pluto is about 6 billion kilometers from the sun. So 20 billion kilometers is not much bigger than the size of the solar system. It's a very, very close approach.
That is tight, isn't it?
It's very tight, but that's the crucial aspect of this story. But it's still, because this thing's in orbit, it doesn't get sucked in by the black hole. It just carries on whizzing around it, passing within 20 billion kilometers. I think every 16 years, if my recollection is correct, that it's got a period of rotation of 16 years. So that's fantastic stuff, and these observations are stunning. But they also allow us to test general relativity, the Einstein theory of gravity. Why do we want to test that? Because we test it all the time. And the answer is because we're looking for something to go wrong with it. We're looking for a place where it doesn't work.
Yeah, we're looking for dints in the theory.
Exactly.
And reasons to prove Einstein wrong. And I don't think we have yet, have we?
No, we haven't. In fact, it's come through every test with flying colours. But why do we want to prove him wrong? Because we want to find new physics. We believe that the theory of relativity is not the end of the story. There are certain things within it that we don't understand, especially when it's related to quantum mechanics, which is the other fundamental theory of physics, the one that deals with the very small. General relativity tends to deal with the very large, and the two are kind of more or less incompatible. So there's something wrong somewhere, and that's why we're always probing these theories to try and find flaws in them that would open up possibilities of there being new physics. And new physics is really interesting because it could include higher dimensions and all of that sort of thing. So that's why people are interested in testing general relativity. How do you do it with a star that passes close to a black hole? Well, the thing is that the space around the black hole is very highly distorted by the gravitational attraction of the black hole itself. So you've got this star that's passing through distorted space, and it behaves accordingly because of that. And the crucial thing is that if relativity was not working and it was just Newtonian dynamics, the theory would all fall over. The star, you wouldn't understand why the star was behaving like it does. in this extreme gravitational field. So the fact that it behaves exactly as relativity predicts, and by behaving, I'm now talking about the speed it reaches as it goes past the black hole, and things of that sort. That once again, as I said, demonstrates that so far we haven't found any cracks in general relativity, which is, on the one hand, annoying, and on the other hand, a major triumph for Einstein himself.
Yes, indeed, yeah. And as I keep saying, he was just a man way ahead of his time. I mean, what intellect to come up with something that all these years later still cannot be proven wrong.
Yeah, that's right. Yes, it's really remarkable stuff. Eventually, I'm sure there will be something that will open up that will reveal that, yes, that's something we don't understand, and we've got to think of ways of testing it.
Wouldn't be dark energy, would it?
Well, dark energy is one of the problems that we don't understand.
Yeah, I know. I was actually listening to an astrophysicist only last night discussing dark energy and dark matter, and he's studying it. I can't think of his name, but he's studying it. He's trying to unravel the mystery. So there's a lot of work going on in that area.
Yeah, there is, absolutely. And those are two things. I mean, dark matter we understand better than dark energy. Dark matter is clearly some kind of species of subatomic particle that we haven't found yet, and so that's kind of down to the particle physicists where they collide with their colliders and things to get to the bottom of it. But dark energy, an energy of space itself, we really don't have much in the way of clues for that. And relativity is probably going to be the road in that leads us to understand that.
Fascinating. Okay, Einstein's right, and never the twain shall meet.
I might just mention, Andrew, in conclusion, that the telescopes that Reinhardt uses for his observing, they are the large telescopes of the European Southern Observatory at Cerro Paranal. ESO, the European Southern Observatory, and of course, as we've discussed before, Australian astronomers now have access to those because we have a strategic partnership with the European Southern Observatory, which is a great thing.
Yes, indeed, very good. Can they access them by remote, or do they have to actually fly halfway around the planet?
Actually, a lot of scientists do go down to Chile to observe there. It's quite an interesting place to be, but you can, yes, there is remote access as well.
That's very handy. You've got to love modern technology. It's made things a lot easier,
That's right.
Including recording our podcast, I might add.
That's absolutely right. We couldn't have done this 10 years ago.
Indeed. You're listening to Space Nuts with Andrew Dunkley and Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated number 1 by Tech Radar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree, and governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, we're going to look at radioactivity in space, nothing like pigs in space. Sorry to the Muppet fans. But radioactivity in space, and more specifically an isotope known as aluminium-26. Now, we could be in trouble here because aluminium is the way we say it and spell it. Do they call it aluminum-26 in America?
I'm sure they would, yes, that's right.
I thought they wouldn't. Anyway, they do. All right. So for the Americans amongst us, aluminum-26 is the isotope we'll be referring to as aluminium.
It's a great story. And actually, I think for the first time, Andrew, you and I are doing 2 stories that come from the same institution, because this is also work that has been done using the facilities of the European Southern Observatory down in Chile. But these are very, very different facilities, because these observations have been made with an instrument called ALMA.
Yes.
ALMA, which we've spoken about before, is the Atacama Large Millimeter Array. And the ALMA telescope sits on a hillside at a height of 5,000 meters. That would be in the region of 15,000, a few more, 15,000, 16,000 feet.
Yeah, you've been up there, haven't you?
Yes, I have. Yeah.
How's your breathing?
It was terrible. I really felt quite ill because what we did. So the ALMA site is on the. As I said, it's on a mountainside, and you normally access it from the bottom end of that, from a main road that leads from San Pedro de Atacama, which is the city in that region. But I didn't have access to it because I hadn't arranged to go and see it. So I thought I'd try and get in the back door. And to get in the back door, you go over this mountain pass, which touches 5,000 meters. And we kept on driving, and somehow we missed the back entrance.
Oh, no.
Probably because by then we were all half unconscious.
Yeah, well, that's altitude sickness, isn't it?
It was, absolutely. I was really glad when we turned back and started getting down to lower altitudes. I've been at altitude before. I've worked at 4,200 meters, which is 14,000 feet up in Hawaii. But this was just another 500 or 600 meters was enough to make it really difficult to breathe, and I really felt very uncomfortable. So I was glad to get down, even though I didn't see the dishes of ALMA. So ALMA sits in this high mountain site. Why is it so high? Because it's to try and get the telescope above as much of the water vapor in the atmosphere as you can. And by telescope, I mean this array. I can't remember how many there are. There's a big number, 50 dishes or something of that sort on the ALMA site. It's a large facility. So they've been doing fabulous work. We've reported on some of it before, but this particular story concerns what's called a stellar corpse, the leftovers of a collision between 2 stars, which took place in 1670.
Oh, yeah.
Yeah, so it was observed at that time, clearly by people with very crude telescopes then. There's nothing like what we have today. It was a bright red new star and visible with the naked eye, but it did fade after a few days. And now all that's left is a sort of stellar remnant that you need a pretty powerful telescope to see.
Is this the one the Chinese observed and reported?
No, that was...
doing that.
That was a supernova.
And
yes. This is it's actually rather hard to give it a name, because a nova, which is the old word for a new star, a nova is fairly specific now in terms of the way it forms. It's usually a single star that does peculiar things, whereas this is definitely 2 stars colliding. So it's just really a stellar collision. So what's happened is that there is this, dim star remaining there, but it's got this nebula around it, a kind of, halo of material that's glowing because it's still excited by the energy of the collision, and that's sort of flowing away from the central star. So what has now been done is a group led by Tomasz Kaminski. They are at the Harvard-Smithsonian Center for Astrophysics in Cambridge, United States of America. And they've used this telescope and actually another one, the Northern Extended Millimeter Array. I'm not sure where that is, actually. I should check up on that.
It'd be north.
It will be north with a name like Northern. Yes, that's right. So they've used these facilities to look at the exactly what's going on in this debris from the collision. And the surprise is that they've found a signature which can only come from a radioactive version of aluminium or aluminum, an isotope known as aluminium-26. And this is what makes this exciting. It is the first unstable radioactive molecule, because it's bound with another element, definitively detected outside the solar system. What we mean by an unstable molecule is one that has an excess of nuclear energy, and so that allows it eventually to decay. So radioactivity, of course, is something that happens to these interesting elements, but they eventually settle down into a more stable form, sometimes over a very long period of time, like we think of plutonium with these long decay times and things of that sort. I don't know what the decay time of the half-life is the terminology, isn't it? Aluminium-26 is, but they're finding the radioactive version, which is very, very interesting. It tells you, that we've got good means for finding these rather exotic molecules in space.
Which could teach us a lot if we expand that search and maybe find other elements, other things.
That's right,
Yeah.
Exactly. Because and it's particularly a feature of being able to use the millimeter radio telescopes, because they look at molecules, they look at the way they're structured, they look at the things inside them. And so even though this object, whose name, by the way, is CK Vulpeculi.
Nice.
I think Vulpecula, if I remember rightly, is the constellation of the fox. I think that's what it means. I might be wrong there, but I should check that. This object, CK Vulpeculi, which is about 2,000 light years away, it's a long way off. It's not a nearby object by any means, and yet we can find these interesting atomic structures within it. It's a great testament to the work of these astronomers and to the engineers who built the telescope at 5,000 meters.
Yeah, well, and somebody with a sense of humour wrote the headline on the European Space Observatory website, "Stellar Corpse Reveals Origin of Radioactive Molecules."
Yeah, I actually like the Thomas Kaminsky, the lead scientist on this. I like his quote, which is, "We are observing the guts of a star torn apart 3 centuries ago by a collision." That's good stuff.
It is. Oh, and by the way, 66.
The number of dishes.
Yes.
There you go. Well, I wasn't that far off. Yeah.
I had to do some stealthy typing. Have you
good.
ever tried to type without making it click?
That's very good. I can't type whether it clicks or not when I talk.
I had 3 cracks at it before it actually found it.
That's good. 66. I remember.
66 dishes at Alma. Which is a pretty nice restaurant too. You're listening to Space Nuts. Fred Watson here and Andrew Dunkley there. Or is it the other way around?
Oh, it could be. Who knows? It's a quantum effect,
Indeed.
3, 2, 1.
Space Nuts.
Okay, Fred, it's question time, and we've got a question today from Richard Goodman. We've actually got 75,000 questions from Richard, but we're going to tackle 2 of them today because that's all the time we've got, folks. But we might get to some of them, the other ones later, Richard, because you're obviously a very insightful individual, and we've found your questions quite exciting, to be honest. But let's get into the first question and we'll see if we can tackle the second one as well. Love the show, especially the in-depth answers that are still understandable. Well, thank you. Fred tries too. I have some quick questions. Actually, you do have quick questions. They're only just slightly shorter than question time in the Australian Parliament. A question came to mind after listening to the last episode where you mentioned the halo of stars around the Milky Way. If you were to view the galaxy from one of these stars high above the galactic plane, would you get a beautiful vista of the central bulge and spiral arms stretching out across the night sky? What a magnificent sight that would be. Would it also mean, depending on the orientation and season, that you might have a night sky almost completely devoid of stars as you look out and away from the galaxy? Fascinating question, and you know what? I've also wondered that too, Fred.
Yeah, it is. I mean, one of the I guess one of the frustrations that astronomers have is we've got a pretty good idea of what our galaxy is like, and Richard mentions it perfectly. They've got this disk of material, which is mostly stars, but lots of dust in there, and nebulae and everything, all the things that we're used to looking at. That disk has this bulge in the middle of it, which is a sort of thickening of the disk. The bulge is a different stellar population, actually. It's made of pretty old stars, which are yellowish compared with the bluish younger stars of the disk. But then, in addition to that, is this
which is what happens when you get older. Things go yellow.
You go yellow, that's right. Yeah, if you go too yellow, you've got to seek medical help pretty quickly, I can tell you.
Well, that's that extra bottle of port or red wine. That's what's happening there.
Yes. Oh, that's all true. And so there is also this halo of stars. Now, the halo is a region of the galaxy which we don't often talk about. You and I have talked about it, and clearly Richard picked up on that. But it is much more sparsely populated. So it's not like the disk, which is full of stars. The halo does have lots of stars, but they're far fewer than in the disk. So if you were on a planet around one of those stars in the halo, particularly if you kind of directly above the bulge of our galaxy, so that the disk was at right angles to your line of sight. Richard's absolutely right. It will be a stunning sight to see with the galaxy laid out before you. You'd see the spiral structure in the spiral arms. We believe we know what that looks like because of infrared and radio telescope observations. But you'd see the bulge. You would basically see the whole thing laid out like a map in front of you. It will be a very enviable place to be. And then, exactly as Richard says, if you look the other way, what do you see? Well, not much. You'd see the sparsely populated outer edges of the halo. There will be a few stars in the sky, but you get a very unimpeded view of the universe at large. You'll be able to see the galaxies in great detail.
Well, that's what I was going to say. You wouldn't see nothing. You'd see galaxies. It'd just be a very different view because your observations wouldn't be polluted by what's within our own galaxy.
Yeah, we get a hint of what that would be like from our vantage point within the disk, because if you look at right angles to the disk, two regions of space that we call the North Galactic Pole and the South Galactic Pole, we astronomers are very familiar with all this. But if you look in those directions, you're looking out of the disk of the Milky Way, so there aren't too many stars there, and you do get the best view of galaxies. But it would be like that, but even more so, in the situation if you were sitting on a planet around a halo star somewhere. It's a great question, and it's fascinating to think of what that would be like.
Oh yeah, and we can only imagine. But obviously, Richard has imagined, and you have confirmed his suspicions, Fred. So that's good. Richard also asks, and this is sort of a throwback to something we were discussing last time, with Jupiter now having 79, I think it's extra moons, how big does a lump of space rock have to be considered a moon? Is it possible for a moon to have its own moon, or will the planet fling it out of the way?
Yeah, it is actually 79 moons.
Oh, is it? Right.
Yeah. So we found.
We found an extra 12. That's right.
Yeah, that's right.
Yeah. Sorry, Richard. Sorry. Should not have doubted you.
One of which is only about a kilometre across, and that's the one that is in a clump. It's in a clump of other moons that have been recently discovered, but it's going in the opposite direction. So its chances of survival are not that great. The question that Richard asks: how big does a lump of space rock have to be to be considered a moon? That's a good question, and I don't believe there is any definition of the lower limit of what constitutes a moon. Nobody says, well, a moon's got to be bigger than...
Oh, well, hang on a second. I mean, they obviously have a definition of what a planet is because they decided Pluto wasn't one. So, and yet they haven't defined a moon.
Well, I mean, in a way, what you're talking about is a satellite. The technical term is a satellite.
Right. Okay.
But we normally think of satellites as being bits of machinery that are in orbit around the Earth. But a satellite is an object which goes around a planet. And no, there's no real definition. But there is a generally accepted terminology. So if you go to the planet Saturn, Saturn has billions, gazillions of satellites going around it, some of which are no bigger than a pea, but we call them the rings. We don't call them moons of Saturn. We specifically refer to the debris within the disk around Saturn as part of the ring system. And I guess that's true with Jupiter. We know that all the giant planets have rings. Saturn has the most spectacular system of rings. The others are pretty feeble in comparison. But the material within those rings you would not normally think of as individual satellites, probably because they don't get any bigger than about 10 meters across. That's the biggest, we believe, the biggest chunk of material within Saturn's rings. And of course, as you and I have mentioned before, there are satellites embedded in Saturn's rings. There are moons that actually move within the rings, and they may have coalesced from ring material. So Richard's right in pointing out that there is a really interesting, and perhaps untidied up definition.
Yeah, we've got to fix this.
Yeah, well, I'm your local representative of the International Astronomical Union, which is the organisation that does that. So leave it to me, Andrew, and Richard will fix things up.
Yeah, well, we'll call it the Goodman theory.
The Goodman limit, that would be it.
That would be, yeah, that's good. I think we should.
Anything below 10 meters is not a moon. The other of Richard's questions: is it possible for a moon to have its own moon, or will the planet fling it out of the way? I'm not actually aware of any known natural satellites of satellites. Of course, there have been artificial ones, and there still are, because we have spacecraft in orbit around our own moon. Those have been put there mostly by the Americans, but also I think there's an Indian spacecraft in orbit around the moon as well. I can't remember. So that's a satellite with a satellite. But in the long term, Richard's probably right. The gravitational interaction between a moon and its parent star results in instabilities, basically, between the two objects, which could essentially get rid of the moon. Okay. It would be very interesting. I'll try and find out if there are any known natural moons of moons, but I don't think there are.
All right, interesting. Yeah, I've never considered the concept. We have binary stars and things like that, but it's obviously different when you've got closer proximity and smaller objects. And and by the way, that Indian satellite is Vindaloo 2. I'm kidding.
I know you are.
Thank you, Richard, for the questions. We didn't get through them all, and I'm just scrolling through my email at the moment. I'll get to the bottom in a couple of weeks. But we may be able to answer more of your questions down the track, and we certainly do invite people to send their questions into us via Facebook or whatever platform you find us on. Just bear in mind that we've got to answer Richard's questions first, so we'll get to yours in about 2027, I think. But thank you, Richard. We really appreciate it. And thank you.
Richard's going to turn off here. He's asking good questions.
Richard, you just got to get used to my Australian sense of humour. It's and the fact that I do a daily radio show and I tend to say stupid things all the time, which regularly get me into trouble. So apologies in advance. But thank you anyway, and thank you, Fred, as always.
Great pleasure, Andrew. Good to talk, and we'll speak again soon.
We will indeed. That's Fred Watson, astronomer, who joins us weekly on the podcast we like to call Space Nuts. We appreciate your support, and don't forget to tell your friends. And we'll catch you next week on, of course,
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.